Thank you very much for the introduction, Jesse. I appreciate it. So today I'm going to be covering ML, basically different types of deployments that you can use in big physics. But well, Jesse covered a lot of it. One of the things is that I've worked a lot with FPGAs and embedded systems. So a lot of what I'm looking at is ML at the edge, which is the phrase you're probably hearing all the time now with 5G and 6G. Also, you're starting to see more of this used in financial systems, a lot more custom devices for pulling out RF signals, things like that. Recently at Radiosoft, I've been working on ML tooling and accelerator device integration. And that includes everything from device drivers, toolchain development, interfaces, things like, is this going to be a network device or is this going to be an accelerator, which we'll get into a little bit coming up, and also some systems level design issues. So we're going to start with systems. Specifically different types of systems architectures that you have and what you're working with, and then go into a little bit of ML development in the ecosystem, which is currently very complicated and very elaborate. Moving on to a couple of tracking workflows and then some deployment workflows before walking through a couple of quick examples that we have. So, why is systems architecture important? And one of the big things that's often forgotten in these discussions is that Google Colab, for example, is extremely popular. But underneath Google Colab is an enormous level of engineering and programming work that's gone into it to make it easy to use and integrate with Jupyter notebooks. Same with AWS SageMaker and a bunch of these other tools that are out there. And this also includes Radiosoft's Repo framework, which we have in place, which we've been using for AI development on our side. And it really makes that engineering work is something that needs to be considered when you deal with systems. And especially when you start getting into a different definition of systems, but the deployment that you're looking at. So what you're seeing here is one of our projects, which is a Cerepo Blue Sky interface, where we're trying to integrate our Cerepo engine with data being streamed in from various experiments and sources, and we want to be able to process it. And you can see that this is a multi-stage, multi-step, relatively complicated system where every type of data that you get is going to have its own pre-processing, its own post-processing. You're going to have different data formats, different data flows. And that's very different from a more straightforward control style system where the data goes in and the data goes out. But you still have to readily consider here, more so in some cases, what error conditions are. Things like, what if a device drops off? Do your outputs need to continue running at a safe level? Do you need safety limits? And often these sort of architectures require lower latency. We're talking going from processing data in the cloud where you might be able to take have it ready in a minute or ready in 10 seconds, for example, to a control style system where you might need it within 100 nanoseconds to be controlling something, depending on your bandwidth. So what do they need to do? Well, different accelerators are better for different use cases. So there's a bunch of different types of machine learning that you need to consider with an accelerator. You have images, you have the controller architectures, you have time series, and there's really a bunch of different ways of doing machine learning, not just considering neural networks. You got Bayesian classifiers, k-nearest neighbors, support vector machines, and then your artificial neural networks. So a quick overview of them, because it makes a difference in how you consider your accelerator and the type of math that you're doing. You have convolutional networks and multi-layer perceptrons where you're taking a bunch of large data and you are pushing it down through a bunch of layers into something that gets you what you want out. A convolutional network takes a kernel, it's called, where you take a look at certain data and then you run this kernel through all your data to see what relationships there are between each. And what you can see in our graph in the bottom right is a recent project we have where the color represents weight. And it really highlights how certain nodes and certain input variables have a much greater effect on what sort of output you see. For example, let me just see if I can annotate. There we go. Take a look right in the middle. You can see some of those nodes have barely any effect. And that makes a big difference for an accelerator where you might not actually want to include those nodes in the calculation when you are doing the math to simplify the problem and speed it up. And all of this, if you look at the left, involves a significant amount of multiplication and often also some form of addition or subtraction, take it what you will. So next style of network, you have a recurrent network, which does the same thing, but the data that goes out also has to feed back into the network. So that leads to needing to look at how your physical architecture of your device can feed the data back in. And one of the operations that you see, for example, is something known as a softmax, where you take the max of a large block of data. And for example, doing that in hardware is much more of a challenge because you need to compare every single bit that you have coming out in a matrix and choose which one is the largest. And that often is done on a CPU, for example, instead of in the hardware accelerator, which can really slow you down. We have transformers. This is the new big thing, using a feature called attention, where each node basically decides what part of the data it's looking at and decides what to do. This is being used very much for the top of the line translation and text prediction things that you see nowadays. So how do you take all of these and you put them into one accelerator? You don't. So what is an accelerator? Well, if you're running something locally, you're probably using your CPU to serialize a bunch of instructions that then get fed down through the CPU linearly. There's also a GPU might be doing that, which can parallelize a bunch of operations, similar to a bunch of CPUs thrown on one thing, but a little bit more efficient. But these accelerators can really save you power when you create something specialized for a purpose. So what you're seeing here is the world's best Go player. On the right side, you can see AlphaGo 0, which is considered to be the world's best Go player at this point. And previously, it took 40,000 watts, which is an enormous amount of power when you think about what goes into that. And with the TPUs, tensor processing unit designed to do the matrix math, you can specialize the operation and use significantly less power. So that is the main reason for using some sort of accelerator in the aggregate, is to minimize power usage using specialized hardware. Another big reason is latency. And there are three types of accelerators, really. You have an inline, you have a co-accelerator, and then you have a general purpose device. Some of you might have seen for the CMS experiment, they're using a tool called HLS4ML, which can take a machine learning model and process the code of the model into something that then gets compiled into code that can be put onto an FPGA or into an ASIC, an application-specific IC. And these are definitely able to reach the lowest latency, but they are highly specialized. And that means that the data that goes in is very much designed for the specific architecture that you do, and the data going out the same. But they can also have the lowest power usage because it is that specialized. What you're seeing here is where they're pushing it into a Xilinx FPGA to reach 100 nanoseconds of latency, which is great for their trigger networks. The other thing we have is the use for ASICs. This is from Fermilab, where you can see at the top, that's where HLS for ML was used. Stands for high level synthesis, apologies, for machine learning. But for using this, there's a bunch of specialized tools that you need to use around it to make sure that it will actually work once you push it out to hardware. And you can see a bunch of this here where, for an ASIC, for example, you have power analysis the whole way down. You have quantization, where you need to decide on the data types of all the data going in and out. You have simulation, you have gate level simulation. You need to build a whole test bench around it to make sure it works safely. And you're not going to spend, $2 to $5 million to push out a specialized device until you're sure that's good. And a lot of these tools are not easy to use. They require a lot of specialized knowledge and a lot of support framework around them. Co-accelerators, on the other hand, are significantly easier to use, and there is a lot of work right now in standardizing the drivers to interact with them. What is a co-accelerator? Well, on the left here in yellow, you can see an inline accelerator, and on the right is a co-accelerator, where the processor is at the top and can send data to this co-accelerator and basically treat it as another CPU. So it streams data into it and you get your results out of it. These are giant matrix multiply units, just general matrix multiplies usually with specialized design to handle how the data flows. And they have variable latency depending on the model and the bandwidth and everything else. But there's significantly lower power usage because they're specialized. The workflows for these rely on vendor libraries because you're relying on the vendor to tell you how to build something to run on this device and compile it and work with it. Finally, you have your general purpose devices like a CPU or a GPU, which generally speaking is the simplest programming model. You just program it and use some libraries that are probably installed on your system or readily available, and they will just work. But they use a lot of power. I think the newest NVIDIA cards are able to pull like 550 watts. It's a much higher level compared to Google's Coral.ai co-accelerators that might pull only 2 watts and possibly get the same, not quite the same performance due to size, but get very close performance for a small model in significantly less power. So how do we manage all this? On a large-scale facility or a large-scale experiment, you're probably going to run into all of these. Because it's really easy to program something for a GPU, but it's not so easy to program something for an accelerator and version control it and make sure everyone's using the same tools and such. So there's there's several development ecosystems that you need to support. One way to do it is to take your facility and say, okay, we're going to require everyone to use the same tool. And because of how the ecosystems work, that doesn't work great because each one is more specialized for different things. Currently, PyTorch and PyTorch Lightning are probably the most popular in some ways for experimenting on science stuff and playing around with things. Keras is part of TensorFlow, which is also extremely popular, and Google supports TensorFlow and Keras. Caffe, which is an older framework, ONNX, which is a standardized runtime and toolkit for supported by Microsoft for deploying and handling models, and TensorRT is another one. And you're starting to see the rise of more machine learning specific pipeline tooling. Okay, so now we're talking deployment. How are you taking these models and pushing them out? Containers, the idea that you can just spin up a new machine that has set versions of all your tools is extremely popular and makes it extremely easy to have an ecosystem that is set up correctly for what you want to do. So KubeFlow is designed for Kubernetes. And I'll show an image about it later. It's a particularly complicated toolchain in some ways, but it supports all the different steps that people want to do. For example, experimenting on notebooks, saving a model, pushing it out to something to serve a model, and then actually serving it. MLflow which is one I like. It's really easy to spin up and use. And it will track your experiments, as they call them, where you'll say, do an experiment for, let's say, segmentation for a laser sensor, where you're trying to determine multiple spot sizes or determine whether or not the laser is off center by doing Zernike or moment analysis on it. And you could just run your model, and it'll push something up to the tracking server and say, hey, we ran this model and it succeeded with these metrics. Also, if you're in the cloud, there's AWS, who has their framework called AWS SageMaker. There's Microsoft with Azure ML, and Google with their whole framework with Google Colab and some other tools you push up from them. But they're all very manufacturer specific. So you don't really want that in your facility unless you're going to move to their cloud. Flip side to is data management. And this has a couple of parts. One thing I don't have on here is a system called DVC. Many of you might have heard of Git. Git is used for version controlling text files. It's very good for text. But once you start getting into binaries like data, you need to start considering, well, how do you version the data? And how do you create data pre-processing and post-processing pipelines where you can consistently and easily say this set of data is going to be processed this way. So DVC is a tool to do that. It works with Git and a set of configuration files. Related to that is that the systems doing the data processing also need to be managed to make sure that they function the same, and you don't have strange issues where one version of the code will read a file from left to right, for example, instead of from right to left, specifically on the byte level. And this happens all the time, big endian versus little endian issues. There's also device management, where you want to make sure the computers and processing nodes all have the same versions of everything. And there's a few tools for that. Puppet is a configuration management tool that will keep machines with all the same versions. Another one is BigFix, for example. And you also need to be able to have a framework in place for management, like Ansible, that will go out and allow you to run scripts on hundreds of machines. So if you have 100 accelerators, you need something that can run on 100 devices and make them all act the same and have the same model version. At Radiusoft, we have a backend that we use to manage everything in our Cerebro framework that is basically homegrown custom. And even if you used any of these tools, you're still going to need a framework of scripting around them. And it is not an easy task in terms of engineering and management to keep all this controlled. The other thing you have is model servers and model runners, where you need a place to version your models. And a model would include all of the different weights and all the different biases for every single node, and have a set of stages where you can deploy it in different ways. So this is called MLOps, machine learning operations. And the idea is that you have to maintain the data model, and you can see here the loop that basically happens with every machine learning thing that you're going to do. You collect data, ingest data, validate the data, and then on the other side, you're going to train a model, evaluate the model, and then you have to actually validate the system that you deploy to, and then deploy it. So NVIDIA has a new tool with, it's the Triton model server, there's a bunch of new paid versions of the model servers and model runners as well. And another one is Argo Workflow, that's part of this little tool chain. I keep throwing in this little K3 AI. This is an open source project run by one person that we're also looking at, that lets you just run K3 AI up, K3 AI run a model. And it's really helpful to quickly spin up a development framework that tracks everything you do, but it still has some bugs. How do you make it easy for people is really a problem. So it's all linear algebra. And we need to figure out, how do you make this easy? So mapping it to hardware is a challenge, and it's difficult to get across to most people the difference in development for software tooling versus hardware tooling. Hardware tooling is probably 20 years behind software tooling in terms of ease of use, mainly due to locked-in vendors, and that hardware is just there's less of it in some ways. So what you're seeing in the bottom right is Google's TPU architecture, and that is a systolic array where the data gets pushed in and then gets shifted out. And that's a standard architecture, but it doesn't look anything like how you would do it in software, because it's all parallel. And because of this, maintaining key metrics is really hard when working in a hardware environment, because at each stage of the process, something is changing the model. You're going to have accuracy change. You need to visualize whether or not anything major got removed or added. And you want to measure power usage as well, because once, let's say you're a telecom, or honestly, if you're CMS, and you want to push out the same model to 1,000 FPGAs, you also want to know how much power that thing uses. And it's very difficult to get accurate performance metrics at high data rates as well, because once you start streaming data in at terabytes per second, your data metrics might be 5 terabytes per second coming out of that, and you need to decide what you want to look at. So optimizing it for hardware, saving power, saving things. This has been a huge project, and there's a couple of major things going on right now in the community, including new intermediate representations. When you compile code, it takes it, turns it usually into an abstract syntax tree of directed nodes, how everything's related, and turns it into basically a new language that then gets turned into assembly code for CPU or GPU or anything else. A few years ago, actually almost a decade at this point, a little bit more, you have polyhedral techniques that showed up, which help with automatically detecting loops and detecting relationships between variables in code. And this is starting to be used to identify regions that can successfully be accelerated. And it allows you to balance the data movement time and the energy versus the acceleration that you'll get from pushing it to a co-accelerator or a specialized device. There's just too many APIs and complexity right now, which you can see here, where, for example, TensorFlow has the ability to push out to 5 different languages at the time this paper was written. This is 2021 paper from MLIR, which is a new intermediate representation as part of the LLVM project. And you can see that there's just a heck of a lot of layers involved, and being able to track all those changes is increasingly problematic. So a lot of people are moving to use the LLVM-IR, which is a major compiler framework, and that intermediate representation is kind of becoming the standard in a lot of these tools for how to move forward on analyzing all this. So there's a need for new descriptions, and we're still working on it. On the right, what you can see is the Circuit project, which is a language designed, it's an intermediate representation and group designed to export the MLIR language to hardware accelerators directly. And they're still figuring out which one is which and what we want to look at, but they meet every week, and they're starting to get to the point where you have a one-button push to go from standard C or C++ code down to hardware and have it work and not have it require an increasingly complex build process. Currently, it's not there yet. Just installing one of their tools and tool chains might take versioning 10 different other tools and getting the right git commit and building LLVM twice to do it. So another project that is increasingly mature is called SciCL. Some of you may have used OpenCL, which was a standard framework for parallelizing code. The new one is SciCL, which is better designed as a language to identify acceleration and help with memory mapping. And you can see the SciCL source code now can be pushed to almost every device that anyone can think of. Tricycle is the open source testbed that increasingly can push to any open source Xilinx code or other open source device, and is being used to really allow for increasingly easier to code parallelized projects. There we go. So for scientific codes, this is a way to pretty quickly convert your code over to something that might run on almost anything. If you can get it to SciCL, you can run it on almost everything. Now this is memory sharing, not MPI, and that's a whole nother complication. So in terms of deployment, I'm a big fan of saying, look at the workflow and figure out how it looks. So we have a couple of examples that we're going to, I'm going to walk through a few more slides after this, but walk through we'll add it to our YouTube video later that sort of show how these processes work. And please ask questions about them. One of them is inference on an edge accelerator, where you can take a model, compile it down, throw it onto an edge device, and push it out. And another one is versioning with MLflow. There you see in the bottom right the issues with Kubeflow. It's a great tool. All of these are great tools for what they do, but they can be extremely complicated. Every single one of those little blocks in the applications is a separate system that runs in Kubeflow. That's how Kubernetes works. So let me see if, yeah. So these resources are links to some very good Xilinx DPU walkthrough and an MLflow example. One of them, the Xilinx wiki, has some amazing examples of seeing the difference in performance metrics between co-accelerator and non-co-accelerator, up to 100 times benefits, as well as some of the pitfalls that you run into in the process. And MLflow works with something like 10 different frameworks, multiple deployment backends, and Azure and AWS, for example, where you could just type MLflow deploy and push out your model. So let me quickly shift over. I want to pop one other place. So what you can see here is one of the Zinc boards. The reason I wanted to pop it up and show it is that these boards are not that expensive. And while the hardware chip on it might currently cost $5,000 if you buy one with a 50-week lead time, the boards themselves are available right now with anywhere from 4 weeks to 10 weeks. And you can readily test models and test things on them. So other than that, we also have the model that I'm going to show in an example that we'll push up, where you take images in, process it using the DPU co-accelerator, and view it on a computer. Going the other way, I just want to highlight MLflow. This is quite a information-dense slide. But MLflow supports a very large number of development platforms, pretty much anything you can think of, as well as custom Python functions. So you could actually create custom calculation in Python, save it up in a server, and if you want to take that and use it elsewhere, just have your code call to the server and pull down a custom Python function and run it, which is a really nice little feature. Other information that we are hiring, Radiusoft is looking for an associate research scientist or engineer. Feel free to pass it on to anyone you know as well. We're doing quite a bit of work across a variety of fields right now. If there are any questions, please feel free to ask them or put them into the chat.
All right, thanks, Josh. Friendly reminder, please do use the Q&A instead of the chat. That helps us keep the questions organized. That was a great presentation. Thank you for your time and effort on that. And we're going to go into our Q&A section right now. So the first question that we have submitted is, what are the best ways to integrate these systems into Jupyter notebooks and workflows?
So everyone uses Jupyter notebooks, it seems like. A lot of these systems will just call into a server and get them. So one of the best ways is to set up your Jupyter environment to have all the functions there for you to just call them and be able to pull down what you want and use them. There is also a Jupyter notebook flow system that's in use at Oak Ridge that Radiosoft has been working with, as well as at Oak Ridge National Lab, to track Jupyter notebooks. And MLflow actually has support for working with notebooks. So if you're going to be using them, you might want to look at those tools particularly.
Excellent. Thank you very much. Next question we have is, what about commercial solutions? NVIDIA and ... others? Question mark.
Yeah, there's a bunch of commercial solutions out there, and there's actually some very good consultants, including Radiosoft. But NVIDIA, for example, has a paid solution, and they're all very solid. It's a question of scale. If you have the people to maintain the workflow in the back end, or if you have that one person who's very good at managing everything, and then explaining it to others, you're all set. But otherwise, really going with someone else to manage it for you is not a bad choice. And I recommend it. AWS is all, and the cloud-based systems are also quite good. So.
Awesome. Thank you very much. We are a 30-minute webinar, and we are a little bit over time, so we're going to go ahead and wrap up for today. If you have any other questions that you'd like to have answered, please feel free to reach out to us. Our contact information is at radiosoft.net. You can also find us on YouTube. Check out our other webinars. This webinar and some supplemental information will be included in that next week at that platform. So thanks everybody for joining us today, and we hope to see you next time. Thanks, Josh.
All right, so what we're seeing here is a raw environment to work with MLflow. And I've already created a Conda environment using Anaconda, using Miniconda really, and installed all the necessary packages. And that includes the MLflow package. So to start off the server, you just do MLflow server and tell it where to store everything, including telling it to store all the artifacts locally. And this is where it's going to look for things that are left over from any of the runs that we do, which we'll see shortly. So I'm going to kick that off. And you can see it's now booted. And you can see in the window below, this is what you see when you log in. And this gives you a list of the experiments that you've done, as well as telling you the state of any of the models and whether or not the run was a success or not. So it's a really nice system to track these things. So to start with, we'll take a quick look at one of them. This, for example, is a run with an awful name, and you can name them yourself, but generally you're probably not going to. You're probably going to go by experiments. And gives you all the parameters that you chose to save with it. In this case, batch size, whether or not CUDA was enabled, how many epochs it took. The other thing it has that's really nice is it tracks metrics. And when you pop these open, you actually get a full graph of the accuracy per epoch, for example. You can turn on log scale, very common if you're doing an accuracy plot or a loss plot. For example, on loss, we're going to go into training loss, and we're going to go into log scale. And there's not much to it on this model. This is an MNIST model that is an example. You can see the loss going down. If we trained for longer, you probably would get better loss. But the accuracy is currently pretty good. So what I did is I saved this model. And this is now a model that is actually in the system
and with 2 versions. So how does this work? Well, what you have is, in this case, a file like this. And the key lines here are that MLflow has what's known as plugins for each of the major toolkits: TensorFlow, PyTorch, Azure ML, SageMaker, you name it, Cafe. And what it's doing is logging information as it goes. So there's the network, and what you can see here is that as it goes, it is doing its logging, and it is logging its weights as it goes back. And the other thing you can see is here, where it makes a point of figuring out what the inputs are supposed to be for the model, so that when you save the model and work with it, you can actually just ask the MLflow API what you're looking for, and it'll spit it out. You also have it logging artifacts, in this case, TensorBoard events. We have it logging the model itself, along with the signature, so that ends up looking right. And we also have all of this wrapped in an experiment name. So what I'm going to do now is go into the MLflow example that we're working with in PyTorch, and I am going to run it. And this is the MNIST TensorBoard artifact example, and we're going to name a new experiment, and we're going to call it, let's see, call it Frankenstein, just for kicks. And no experiment exists. So the cool part is that you can actually tell it to make new ones if you wanted every time you go, as well as run IDs. Okay. So I'm going to run an MNIST TensorBoard artifact example, and we'll see it pop up in our default experiment here. And you can see it was just started, and this one runs pretty quick. And we'll cancel it, and you can see it popped up right here. It says that it was failed, and it's great. So this is an extremely powerful tool because it has a very, very strong, easy API to work with, including tools to actually load the model, where you can just use Python code to load the model that you're trying to do. And this is extremely handy, and that ends up looking like this. This is a PyTorch thing where you need to have the model in there, unless it's a specific type, and all you do is call load model, name of the model you're loading, as well as load model based on the run. And finally, you can go to models, and you actually have different stages. You can have a model that just came in, you can have an archived model, you can have a staged model or a production model, which is extremely useful. If you'll get another model, it even tells you the inputs and output formatting. Now, the reason that I think this is really important is that when you start working with machine learning, a lot of people will just run in and you'll create something that works and does solve the problem. But the problem is that if you don't consider the workflow behind what's going on ahead of time, you can really back yourself into a corner where files are everywhere and you have to worry about that. So that's an important thing to consider. All right. And the next thing I'm going to show you quickly is using the edge accelerator. And this is where the other issue with workflows becomes really important, especially when working with edge devices. You can do everything on Jupyter on a single device, which is fine, except you're going to be logging into it continually, running stuff continually, and you still need some sort of thing to push out to that device. So what I'm going to show here is a full solution that we started with, where we have a model, and you can see that model here under, we have a tuned ReLU model that was saved, which is a TensorFlow model. And this model, we want to convert into something that the Xilinx DPU can use. So we have a whole series of scripts that we have to use for that. Xilinx provides a Docker script in their Vitis AI toolkit. This Docker has to run something that installs all the functionality that we need, including running the scripts to build, compiling the code, and it generates a nice little graph. We have the Python itself, where we set up logging. We pull data out from our initial data set to make sure that we don't lose accuracy. And then we quantize the model. And then we deploy it. And deploying it, you're going to want to push the data set, in my case, the same data out just to see how performant we are on this, as well as running any trace software and then pulling the files back. So this whole process will look like this. And you can see it automatically going out, quantizing everything in the TensorFlow layers. There we go, quantization is done. And it even tells us where the model is and everything else. So if you look in this folder now, we have this, where is it? This build folder. And when you look in the build folder, you'll see the compiled model. And in the compiled model folder, you'll have that SVG that I mentioned, the X model, which is the compiled model for the DPU, and some information about it. So this looks like this model. It's a very small convolutional layer that we saw earlier with just 3 layers. And what you can see is it preparing the data up at the top, reshaping it, putting it through the DPU in this block in the middle, and then pushing it back out at the bottom. So that was 3 of those scripts that you had to use to do this, followed by our deploy script. We have the DPU running there. So we're pushing the stuff out. We are running the VAI trace tool, which provides backup files using Linux trace functionality to be able to take a look at how it's doing. And I think it's done. And then we copy the files. So we've copied the files over. What this gets you is something like this. And this is the Xilinx Vitis_analyzer tool, which is not quite obvious where it pops up. It is called Vitis Analyzer, and you need to make sure to source your Vitis toolkit to be able to do this. It's part of the Vitis installers toolchain. And what you can see here, we're going to reload everything, get the newest data, and here we are. And now we have a timeline that shows what was actually running on the edge device, including where we load the model as it gets loaded into the device. And then as we go on, you can see where it actually starts doing the actual data. Let's get in there. And what you can see here is a single run of an input batch through the model with a load where it writes it to the device. The CPU is waiting while the thing runs, and then we read out the result. And you can see how fast that this runs. This is a very small model, but at the same time, it's pretty performant. And all of this is bandwidth limited, and this is as a co-accelerator instead of an inline accelerator. The other thing about all this is that all this is based on the Vitis AI system. You get there and just make sure that people have some idea how critical this is. So they provide a full toolkit that was just updated recently that includes examples for building the different DPUs, the different demos for all of their different tools, and all the different tools, including the equipment for actually building the Dockers under setup. So it's at least for Xilinx, it's really nice to have a full tool chain there that you can work with, that with full examples that you can base all of your scripts off of. And this does get particularly complicated sometimes when you get into the actual run scripts. So this script is the one I'm using right now. It's just based off of one of their examples. And without having it, you don't understand the libraries that they're using. And it's just a block of code, basically, with the key being in the main thread where you're creating threads and then you're running them. So right here, I highly recommend taking a look at that if you're going to use them. So that's the two examples that I have. I think that these, no matter what you do for big physics, you really have to start from the ground up and figure out, like, all of these are simple to use if you take the time to build them, to build the framework around them. So thank you. Appreciate your time.